Hi everyone. Today we're going to talk about properties of functions, and we're going to first talk about even and odd functions. So out of the two, we're first going to talk about even functions because they are the kind of the easiest to draw and understand. So we're going to look at even first. And so let's look at what even means. So I'm just going to draw some points here at random and just kind of connect them with the graph. So let's look at this function, whatever it might be. It's just something I picked at random. So this is what even means. Even means symmetric about the y-axis. This is what even means. But let's reword this in a different way. I discovered recently this is a good rewording of it. If you change the sign of the x-coordinate, you do not change the sign of the y-coordinate. The y-coordinate remains the same. So let's look at this function. So there's going to be a part that's going to be on the left-hand side here. I haven't drawn it in yet. But notice what points I have. I have 0, -3, 1, -2. I have 2, 1. I have 3, 3. I have 5, 2. And I have 7, 1. So let's see what evenness means here. So let me get a different color here. So let's think about the rewarded part here. So if I change the sign of the x-coordinate, the y-coordinate remains the same. Well, there's no sign to change here with 0, so we'll just leave that alone. But if I change the sign of 1 to -1, so now I'm at -1 here, but the y-coordinate remains the same. So this point is going to go here, and that's going to be -1, -2. So I changed the sign from 1 to -1, but the y-coordinate remained the same. Let's say then what happened here. I will change this 2 to a -2, but the 1 remains the same. I'll change this 3 to a -3, but the +3 will remain the same. This 5 will change to a -5. And we'll have a 2, and then this 7 becomes a -7, and the 1 remains the same. And look what happens here. I get a mirror image of the function on the other side of the y-axis. And that's what it really means. To be even is that you have this mirror copy here of what's on the positive x. So these are all the positive x values, these are the positive y values. So you basically just have a mirror image. And that's why you have this rewording, is if you pick this point and say, well, I'm at 2, 1, but now I want to be at -2, what value of y should I be at? Well, you just come over here and it's still 1. It doesn't matter if it was positive or -2. Same thing here. If you're at +5 and you say, oh, what happens when I'm at -5? Well, you have the exact same y-coordinate because you're a mirror image of each other. And another way to think about symmetric is notice that the distance here from the y-axis is 2, and the distance from the y-axis is 2 here. So notice that also another way to think about symmetric about the y-axis is that the 2 points are equidistant from the y-axis. So this point and this point are equal distance, and if we look at this point, it's 3 from the y-axis. This one here is a distance of 3 from the y-axis too. So equal distance from the point. So basically the y-axis cuts the mirror image right down the middle in half. So, but what does this mean in algebraic terms? So what this means is for evenness, is that, remember that negative sign is the negative is what we use to change signs. So if we take f and evaluate it at the opposite sign, so at negative x, we should get the same thing as if we took f and evaluated it at x. So this is the definition of even. So an example of how to prove something is even is, for example, with f of x equals x squared. This function is an even function because if we draw it, so we'll have 0, 0. But if we look at 1, 1 and change the sign of the x coordinate, well, the y coordinate remains the same. Same thing when we're at 2, 4. If we change the sign of the first coordinate from 2 to negative 2, well, we're just going to be at negative 2, 4. So the y coordinate doesn't change. And so that's why the right-hand side and the left-hand side of a parabola look like mirror images of each other. So, proof of evenness. So what you do is you take f and evaluate it at negative x and see what you get. So remember what we said in the previous video, when we're evaluating at an expression, you look for all the x's and you replace them with the parentheses, and then the exponent always goes outside. And then what goes inside this parentheses is the same thing that's in this parentheses. So we'll have a negative x in here. And then we can square this and we'll just get x squared because two negatives make a positive. And notice that that is our original function. So notice our equality says that f of negative x equals f of x. And that is my definition of even. So x squared is a type of even function, and it's usually my first example. This is kind of a new explanation for me, the way I'm explaining it. It's not a new explanation. I've known about it for years, but it's the first time I've actually used it. So now let's look at odd. And then we'll be done with it. And then we'll have one more example. We'll be done with this video. So odd. Odd is symmetry about the point 0, 0. So that means, so the previous example, the even functions, they were just equal distance from the y-axis. So we're going to have now a pair of corresponding points that are going to be equal distant from the origin only. So let's look at an example here. So let's, let me see. I wanted to say something else. Oh, so the reworded version first before we do the example. Reworded version is this is if you change the sign of x, you also change the sign of y. So let's look at an example of what an odd function may look like. So I'm just going to draw something random on the right hand side here. So I'm just going to pick some random points and just connect the dots. So what I'm going to do, you know what? Yeah, that's good enough. So what I'm going to do is, this function is going to do something like this. Come back up. Keep going like this forever. That wasn't very good, so let's try that again. I'll come down here, at that point, come up, there we go. That looks better. So this point here is labeled let me see, that's 0, 1, 2, 3, 4, 5. This is 1, 1. This is 3, 3. This is 5, 4. And this is 7, 4.5. So 4.5. No, that's awful. 21 fifths. And I'll just write on the side 21 fifths equals 4.5. No, it doesn't. It's not 21 fifths. Oh, it's 9 halves. And this is this last point is 7 9/2. So what we're going to do is see what this looks like as an odd function. So what this says is if I change the sign of this, I should also change the sign of that. Well, sine. Oh, this is a shitty function. Let's try something. Oh, it's through the origin. So I'd better go through the origin. This won't work otherwise. Alright, so I'm going to pick some random points here. So let's see here. We'll pick that one. We'll smooth out. And do something fun like this. Try it one more time. There we go. That looks nicer. So let's label these points. This is the origin. This will be 2, 4. This will be, let's see, 3, 4, 5. So this will be 5, 6, 7, 8, or 6, 7, 8, 5, 9, 10, 11, 4. So what we want to do now is change the signs here. So if I change the sign of 0, 0 sign changes to 0 because they don't have no signs, so that point stays the same. If we change to -2, we have to go down to -4, so we'll be at -2, -4 here. If we change the sign to 5 to -5, we also have to change the sign of 6. So we have to go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So we'll be at this point -5, -6. If we're at 8, so 6, 7, 8, we should be at, or if we're at -8, we should be at -5. 1, 2, 3, 4, 5. And then when we're at 11, so 9, 10, 11, we should be at -4. 1, 2, 3, 4. And if I play connect the dots like I did on the top, I should get an upside down reflection of that graph. Now let me try it one more time. There we go. So notice the way I think about it is first you reflect the image this way. So let me. So you would reflect it this way first, this direction, and then you reflect it down this way. So that's what origin reflection of the origin is. And notice that when we look at distance from the origin, this line here looks approximately the same distance as this line here. And that's not a coincidence. They are exactly the same distance. Just my drawing is not that good. So, and then if we draw a line from here to here, it looks like the same distance from here to here. And again, it is when you draw it, with computer precision. So that's what it means to be an odd. It's these pairs of points are equidistant, and how you tell 2 points are equidistant from the origin is if you change the sign of the x-coordinate, all you have to do to find the corresponding point is change the sign of the y-coordinate. So that's what it means to be odd. So we need an algebraic definition like we had before, And so what that means is algebraic definition is this, is if I take f and change the sign of x, this will equal to the negative of the y value. So remember that y is always equal to f of x, so this is going to be the y coordinate, and if I change the sign here, I have to change this value sign too. Another way people kind of mnemonically put it is that you can pull the negative out in front of the x, which is a good way to think about it as too when you're dealing with this type of notation, but sometimes that can be a little misleading. So let's look at a typical example. That's going to be the f of x equals x cubed function. So, and it has the desired property we want. So let me draw a big graph here, because even at 2 it's going to be big. So we'll have 0, 0. We'll have 1, 1. But we also have this corresponding part 1, negative 1. If I could write the negative. Then we're also going to be at 2, 8. So 2, 3, 4, 5, 6, 7, 8. So here's 2, 8. But we'll also have the corresponding point 2, negative 8. So 2, 3, 4, 5, 6, 7, 8. So here's negative 2, negative 8. And so here's the graph of the function. And notice that when we connect, for example, the two farther points away, this line here looks to be about the same distance as that line there. So let's prove that this is an odd function. So what you do is you take f and evaluate it at negative x. So again, following our previous video, you take this x and replace it with the parentheses. The cube goes outside the parentheses, and what's inside this one goes inside that one. And then since we have 3 negatives, we'll still have a negative, x cubed, and this will be negative the original definition here. So we've shown that f of negative x equals negative f of x, which means that this is an odd function. So you may be asking yourself now, before we end this video, are all functions odd or even? And the answer is no. And so an easy example here to figure out is x to the 5th plus 1. So the trick is to doing any of these type of problems is you always put negative x in and see what happens. Notice here that this will be negative x to the 5th plus 1, which would give me a negative x to the 5th plus 1. And notice that this does not equal negative f of x, because the sign at this point, here, never changed, so we can't factor out a negative, and then this disagrees with the sign here, so it can't be even. So this is a neither function. It's neither odd or even. And most functions are neither. So only special functions are odd or even.